These are all the recent ones. This is near Bangalore very recently. This is in Ajmer some time back. You can see this structure is made with steel strips. Okay, so what we have seen here in all these problems is actually the connection of the fascia panel with the reinforcing element has broken. Why it breaks, what are the issues involved, how do we design it, we will talk about it a little later. But as I said, right now we are only looking at the problem. Moving further, the second kind of issue we have faced is the deep-seated failure, or the, I would say, the bearing capacity failure. And I'll try to give some examples for the same. This is a wall which is constructed on NH2 long time back. And during construction, it settled by almost 3 meters. As you can see, this portion of the wall sank into the ground, and the side ground upheaved. And it was noticed that the wall underwent a settlement of almost 3 meters. This is primarily because the behavior of the foundation soil was not very well understood or analyzed before the construction was taken up. Coming to another issue which we have faced is fascia interlocking or cracking. What it is, I'd like to present to you through some pictures. At times, the fascia get interlocked and the corners start to crack. You can see some more examples. Some more examples. And in case of block walls, this is what happens. In case of block wall, it's not because of interlocking, it's primarily because of differential settlement. But this is an issue which we need to address. And one way of addressing it by putting split joints. And in case you avoid this putting split joints, the problem would come. I'll skip this slide. Similarly, split joints are put across a box culvert construction. And by putting these split joints, we're able to control the fascia interlock. Similarly, for a block wall, presenting you some pictures where you can see the differential settlement very well, that this part of the wall is not settling as much as this part of the wall is settling. And you can see that because of that, the fascia cracking does occur. An example where the fascia cracking is avoided is this kind of construction. As you can see, we have put a split joint here. And if you see it more closely, you can see that this part of the wall has settled more than this part of the wall. Coming to excessive deformation, negative batter, a lot of cases have come up in the recent past. And I'll present to you through some pictures. These are all very recent ones. And mind you, when this kind of construction or this kind of problem appear, there is no simple solution. The solution is only that you dismantle it and reconstruct it. These are all examples of excessive deformation or which results in negative batter. This is a flyover in Delhi, and every time I pass by the side of it, I get a feeling it's going to fall, but it's been standing now for almost more than 15 years. We have also tried a new fascia in India, which is the welded wire mesh face. This is how it looks like from the surface, but this experience also has not been very good. And at times, this has been dismantled and reconstructed. Again, a couple of examples of negative batter. You can see this wall has leaned outwards. And as I said, there is no simple solution. You only have to redo it. Erosion of backfill and vegetation growth are examples of which deal more with the maintenance, not with any kind of distress or failure. But I'll put the point across through some slides. If you do not channelize your water properly, this is what it's going to happen. Coming to vegetation growth, I think we can see, we have seen this kind of problem not only in rural areas but in cities as well, that we have a lot of shrubs and trees growing on our RE walls. Dr. Shade, good so far? I mean, are you able to hear? No issues? Dr. Shade, are you there?
Yes, sir, it is audible.
Okay, fair enough. Let me keep checking, otherwise I may proceed and we may miss the contents. So some bad practices which we need to avoid in RE walls. Here is one of them. We are erecting the crash barrier, and you can see the crash barrier is resting on the RE wall panel, which we all understand that it should not be resting here. There should be some gap which has to be provided. And we all understand that in case the crash barrier is not stable, we do put a wooden block and people come up and say, this is only a wood which will go away or will disintegrate in some point of time. But eventually, this is all transferring the load to the fascia panels, which has to be avoided. And how we can avoid it, I'll come back to you in a little while. You can see another bad practice. The bad practice is that this approach slab is entirely resting on the wall panels. In a while, I'll come to this, then tell you that the wall panels is a non-structural element and it cannot take any vertical load. But this kind of construction will transfer all vertical loads onto the fascia panels, and believe me, we will all be in trouble. Okay, my favorite example. We have a cross wall which is sitting away from the abutment, and we do a gap slab and we do a approach slab, and we put a foundation beam to support the gap slab and the approach slab. What has been done here is that after the RE wall vendor, which happens to be us, we constructed the wall and went away. Contractor came back, broke the panels, made the foundation beam, and then constructed the gap slab and the approach slab. I mean, you can imagine what would happen to these panels in due course of time. Another bad practice, you have laid geogrids on the bed and you're allowing the trucks to ply on it. Another bad practice is that you have not made a bed properly. You've not filled your soil up to the point where you need to put your reinforcement, and you put your reinforcements. You can imagine that once your next layer will come, these connections would undergo unnecessarily excessive stresses. One more thing which you can all avoid is that having any utility duct very close to the cross wall. Mind you, if this cross wall is there, it is very difficult to, if this duct is there very close to the wall, it is very difficult to construct reinforced soil walls. So anyway, the screen has come back again, just in case you joined late and you want to note down the WhatsApp number on which you can SMS or you can WhatsApp me the questions, which I will try to answer in the end. Okay, so that's the first section of the presentation, wherein we did discuss about some setbacks or some failures or some bad practices which we have had. For the benefits of my friends from structural engineering, I would like to review some basics of reinforced soil walls. Just only 10 minutes, which will give you an idea. I mean, you will be able to appreciate better as to the solutions which we are going to propose. This reinforced soil walls are understood by many names: RE walls, retained earth, MSE walls, SRW, MBWs. I mean, they all mean the same thing. The basics of reinforced soil principle, I think, is that once you put some tension elements in a medium which can take compression but not tension, its behavior improves, which is very well understood by this slide also, that if you have, if this is a soil mass and you have vertical stress being applied to this, you need horizontal confining stresses, without which this mass would fail. And this confining stresses are provided by the reinforcements which we put in reinforced soil walls. And the two in combination give you a stable system. Examples of applications: we do walls, we do abutments. When I said we do abutments, here the bridge is resting on reinforced soil wall abutment. There is no pier or pile cap here. Okay, so this is a wonderful construction technique which is not very popular, which has somehow not become very popular in India. And we can do reinforced soil slopes, which we can do at about 45 to 70-degree angles. A typical example of a flyover construction where it has basically three major components. You have the reinforced soil here and the reinforced soil here, and you put the reinforcing elements in layers, and you put a concrete fascia outside so that it looks good. And mind you, this fascia is a non-structural element. This fascia is in place because we are connecting this reinforcing element to the fascia. If this connection of the reinforcing element with the fascia fails, the fascia will not be able to stay in place and it will fall off. And that's what happened in many of the slides I have shown you earlier, where the connection of the reinforcing element with the fascia panel broke and the fascia became unstable. Mind you, that failure is not a failure of reinforced soil wall as such. It is only a fascia separation. But for a general layman terms, that's a failure because one component of the system has failed. Proceeding further, we all understand that if we want to make a vertical cut in a soil, it is not possible to do so, because the moment you do that, a crack would develop and the soil mass would slide out, or there would be a rotational failure. But this can be avoided by putting tensile reinforcements, and that's the basic principle of reinforced soil wall. I'll skip this slide and quickly run through what kind of reinforcing elements we are using to construct reinforced soil walls in India so far. We have steel strips, metallic bar mats, twisted wire meshes, polymeric grids, textiles, and geostraps or geotries or parawebs, whatever name you call them. The first three are metallic, and these three are polymeric in nature. This is how the placement of steel strips looks like in a reinforced soil wall. And these strips, mind you, are not plain. These strips have these serrations basically to enhance your friction. Metallic bar mats are basically mats constructed out of reinforcing bars. We have the longitudinal bars and we have the cross bars, which are spot welded at all locations. And finally, this entire mat is galvanized before it is used as reinforcing element in reinforced soil walls. I'll show you some pictures as to how this is connected to the fascia panel. In the fascia panels, you have these two hooks kind of system which is embedded in the fascia panel, and your mat is connected through a rod here. A closer view here, you can see that this is my bar mat, the longitudinal elements of the bar mat, and we have the hooks already embedded in the panel, and we put a rebar or a toggle bar through the hooks to connect this with the fascia panels. The IABSE ROB, I think we all know it very well. I'll show you the picture before I explain this slide. You basically have the Gabion fascia to begin with as the fascia. So what we have in the double twisted wire mesh is that we have the wire mesh going in for a length of about 3 meters, which is buried into the soil. And the same wire mesh will make you the boxes here, which can be filled with stones. So the same element is acting as a reinforcing element as well as the fascia. You can see the picture clearly here. So the same thing here again. What you have is the box which is filled with stones, and as I said, about 3 meter length of this is embedded or buried into the soil to give you the reinforcing characteristics. And in case your design demands that this is not sufficient, then you can overlap it with more reinforcing elements like geogrids or paralinks to make his reinforced soil wall. Geogrids, I think, is the most widely used reinforcing elements these days. I don't need to tell you more on this. Geostraps is another very widely used variety of reinforcing elements. We call it geostraps or paraweb or geoties or polo ties, whatever name. There are many names by which we know it. So on this end of the bed, these parawebs are anchored to the soil with some hooks here. Idea is that it has to be in a taut position so that there are no wrinkles or there are no slacknesses here. And on the fascia side, it can be connected to the fascia with many mechanisms. The one used here is the cavity connection, or you can have a steel hook connection. So both are prevalent and are being used here. Coming to the skin or the fascia we've been using for the reinforced soil walls, there is a variety of it is available. You can have discrete panels, you can have full height panels, or you can have a wraparound fascia. Out of this, I think this is the most widely used fascia. I'll show you and explain to you using pictures. This is all discrete panels. You have all these as discrete panels which you assemble at site and make reinforced soil wall fascia. You can have full height panels, and as you can see that this is a difficult construction. One more example of a full height panel. It has been used, but for obvious reason, this has not become very popular. We have a wraparound fascia. The wraparound fascia is the one where the reinforcing elements is wrapped back into the soil. The only difference here and the normal walls I have shown you little back is that we don't put a concrete fascia here. In India, this is primarily being used as a temporary construction. When we have a 6-lane project where these 3 lanes cannot be constructed because you don't have space to divert the traffic, what is generally done is that you make a flyover using once the central wall as a wraparound fascia wall. This traffic is then diverted on top, and once this is diverted on top, you have the space available and you can come back and do the another carriageway of the reinforced soil wall construction. So this is more of a temporary construction, which when you do the carriageway construction in this part, this gets buried. So this is a wraparound fascia. And one more example of the wraparound fascia is that you can use sandbags as the fascia, because this is a temporary construction, and depending on how long you expect these reinforced soil, these soil bags to last, for that much of duration, you can easily use this also as the fascia. The welded wire mesh fascia, I showed you some slides a little while ago. Again, this is, according to me, has not become very popular for obvious reasons. And one of the obvious reasons is that this is very much prone to vandalism. Stone-filled gabions, the Derabasti's famous flyover I showed you earlier. Modular blocks is another variety of the fascia which is being used very, very widely in this country. So friends, with that, a couple of more pictures of block fascia to tell you how the blocks are assembled or how they look like. These are my fascia blocks. the cavity of the blocks is filled with aggregates, and also you have the aggregate filter media behind. How the geogrid is connected to these blocks? Very simple. The geogrid is laid over the blocks, and then you place the next layer of blocks. So it is primarily sandwiched between the two layers of blocks, and the connection strength is derived by the friction being developed between the geogrid and the blocks, and also the aggregate infill in the cavity is an additional advantage in giving you better connection strength. So this geogrid is laid over these blocks, and then you come back and put the next second layer of blocks on top of it, sandwiching it between the two. So far, that's the background of reinforced soil walls I wanted to present. Coming to the area of concern, what we need to review and what we've learned in these 25 years of construction, I have tried to list down about 15 points which I could think of. There could be many more, but these were the points which I thought would be of immediate concern. So forget about the 16th point. There are at least 15 points which I thought I would like to present to you. So let's go one by one and see what I have to say about these 15 points and how they have given us trouble and what we need to do to solve the same. So starting with connection testing, I think in our earlier slides, we have shown the fascia separation problems, which I said is primarily because of deficient connection. It can be deficient in terms of design, or it can be deficient in terms of material. There have been situations where, although the connection was properly designed and executed with proper material, then it still failed. And why it still failed is basically because of the reason of internal settlement, which I will talk to you when I come to point number 5. So connection testing is very, very important. And I think as client and as consultants, it's very, very important that whatever connections are being proposed, proper testing reports are available for these connections. And I'll try to present to you the testing through some of the pictures we have taken during the testing we have carried out for the connections we've been using. That is a steel hook, which we use with the geogrids. This is a connection testing of an HDPE geogrid, which is buried in the panel and connected to the polyester geogrid. This is the testing of the cavity connection, which is used with the geo straps or paraweb. And mind you, all these testing pictures I am showing you here is all done by CRRI, that is Central Road Research Institute, and they tested all these connections and came up with suitable reports. This is how a cavity is fixed in a panel, and one more picture of how it was tested. There is one more point regarding connection testing, which is given in our codes, and that testing is with that connection issue is with respect to the use of block fascia. And our new IRC SP 102 says that we should not be using the friction connections in seismic zone 4 and 5. So I will tell you in brief what it means is that this code actually prevents use of block fascia without a mechanical connection in seismic zone 4 and 5. So this is a very, very important point which we all need to keep in mind. NHI has come out with circulars, but it's still, to my surprise, I keep finding that a lot of construction with blocks are still being done in seismic zone 4s and 5, which can be avoided if all the consultants are actually aware of it. And similar recommendations are available in AAStro also. In AAStro section 11.10.7.2 also says that therefore block walls with friction connection should not be used in seismic zones 3 and 4. This is the American seismic zones with the desired acceleration greater than 0.19 G and 0.29 G respectively. So you can see that they don't even allow the blocks where the zone, the seismic coefficient, the seismic zonal coefficient is higher than 0.19 G. And in our seismic zone 4, we know that our seismic zonal coefficient is 0.24, and zone 3 is actually 0.16. So it will be very, very prudent to say that if we follow these recommendations, probably the block walls would not be feasible in zone 3 as well. But I'll not get into that. At least we have a code of IRC which says that at least in zone 4 and 5, you don't need to follow it. I mean, you don't need to allow the block walls with the frictional connections. Proceeding further, approach slab and gap slab. This is my favorite subject. I have already shown you a couple of slides as to what should not be done. Let's start with the basics. We know that generally our abutment foundations are resting on pile caps. The first and foremost thing which we now need to do is that we need to make our cross wall which is away from the pile cap. I mean, I would request every structural engineer present on this webinar that now onwards kindly do not design any system where your RE wall is resting on top of pile caps. Kindly keep it away from the pile cap. The issue of bridging this gap can be solved very easily. Please don't worry about that. But mind you, this cross wall has to be away from the pile cap. And how we can bridge this gap is very, very simple. This is an example in Delhi where for some reasons we could not go very close to the pile cap also. And this gap from here to here became almost 5 meters. And we could still do it. And how it is possible, I'd like to explain to you through a sketch. You have your pile cap, your abutment pier. Please start your wall behind the pile cap. And then you can have your gap slab and the approach slab as one single monolithic construction. The gap slab from here to here and the approach slab from here to here can be monolithic. And the point I'm trying to stress upon here is that the approach slab from here to here should be about 3.5 meters. I mean, let's not make the entire length from here to here as 3.5 meters. The slab which is resting on the soil here should be about 3.5 meter long. And you can make it monolithic with the gap slab. This is shown again here in this slide. This is my fascia panel, the filter media behind. The gap slab and the approach slab can be made monolithic. And very, very important thing is this thermocol to be placed on top of the panels here is basically to ensure that no direct load transfer to the fascia panel. This is a crime if you do not put this thermocol here and you put your structure and you cast your approach slab and gap slab, and then this structure starts deriving its support on the fascia panel. No, the support has to be derived on the fill behind, not on the fascia panel. Okay, let's proceed further and see what we've been practicing. I don't say that everyone is practicing this, but I have seen this kind of drawings where a gap slab is made first, and then you put a foundation pedestal or a foundation beam, and then you put an approach slab behind. I mean, I don't see the reason of this. Firstly, this will fall with the reinforcing elements which are already which are already placed in the reinforced soil wall. And I have come across situations where after we have constructed the reinforced soil wall, the structure team has come back and excavated, removed the reinforcing elements, made this beam, and then constructed the approach slab and the gap slab. There is no need to do that. There is absolutely no need of this kind of detailing to be done. What I request you that you make this approach slab and this gap slab as monolithic, and you don't need this 400 thickness of gap slab also. 300 millimeter thickness is enough to span a gap of in excess of 3 meters as well. So please avoid this kind of detailing. And I showed you this favorite picture of mine, which says that the structure team can come back later on, cut the panels, bake the beam, and then cast gap slab and approach slab. Let's not give them a chance to do this kind of construction. Another construction which we have seen is approach slab being cast directly on fascia panels. And one more eyesore here is this corbel here, which I believe can be stopped little behind so that you don't see this here. And I'll try to show you through some three-dimensional views here. What we're trying to do here is that we're trying to avoid construction of that corbel right up to the face here. Let me show you in detail here. So what we are doing here is that this crash barrier, which is part of the structure of the box construction, that's part of the crash barrier is extended by 300 millimeter on both sides. This 300 millimeter is actually the width of the corbel. And so in effect, if this this length from here to here is 8 meters, my crash barrier length from here to here is 8.6 meters. The advantage of that is that I'm stopping this corbel about 500 millimeter inside. From this side also and from this side also, I'll have another RE wall being done here. And this crash barrier is continued for 300 millimeter more, so that later on when I bring my precast crash barrier, which is resting on the, on the fill on the RE wall, that crash barrier can be started from this point onwards. Well, I hope I'm able to convey what I want to say. One more picture here, that this crash barrier is extended for the width of the corbel, which is 300 millimeter. The corbel is stopped by 500 millimeter inside. 500 millimeter is the width of crash barrier. So this crash barrier for 300 millimeter length becomes part of the structure. And then my precast crash barrier, which I place on top of RE walls, can be placed from this point onwards. So this is another detail which I would like all my structural friends to follow now onwards. It would bring some aesthetics back to this field. Next issue is about abutment annular filling. This is also lead to a lot of problems. Before I get into more details, let me explain to you what I mean by abutment annular filling. When we have to do an open foundation abutment, which is founded at a level generally which is much below the level at which we found our RE wall. For example, in this slide, my RE wall is resting at 414 level, whereas my open foundation is at 411 level. Dr. Shade, are you there? Hello, Dr. Shade?
So I think he left.
No, sir. Sir, I am there, but I was on mute.
Oh, I see. I was just checking that I'm going on, and I hope somebody's listening.
No, sir. It's going very good actually. So I went on mute.
Okay. So just to check that everyone is around. So going back to the issue that my open foundation is generally deeper than my leveling pad, where I start my RE wall. And in the process, what happens is that I do an excavation of this sort. Maybe this line should be going up to this point because this is my OGL here. Anyway, so what I need to do is that I need to excavate this, construct my open foundation, come back, and I need to fill it back with the backfill material. Now that's where the problem starts, that at times I just dump the fill here and request the RE wall contractor to start the construction of the wall. And mind you, this has created, at least for me, in our projects, at least 4 occasions where we built this wall and then came back and dismantled the whole thing and redo it. Let me give you some slides to prove my point. Okay, this is another foundation which was done on open thing, and then a lot of investigation went into it, because you can see that this part of the wall has settled and has rotated towards the right, and because of that, the gaps here start to appear. Can we all notice that? From this point onwards, there seems to be all okay, but this part of the structure, especially over here, these lines have inclined to the right, which means a lot of settlement has happened here. And this was primarily because the backfilling in the open excavated part, which was excavated to put my foundations in, was not filled back properly. If you think this is not very visible, I'll show you one more slide, and I'm sure you can make it out very easily that this 4 panels here have actually sunk into the ground. And because of that, what has happened is that these gaps have opened up, and what we're trying to do here is that trying to fill this up with a lot of concrete. But mind you, the problem does not stop. You keep on filling and you keep on filling, and the gaps keep widening. How much they can open up, I'll try to show you in this slide. How much is this? This is almost 8.5 centimeters. Almost more than 3 inches, the gaps have opened up. And then don't stop. I mean, you could put your entire hand inside and inspect what has been filled behind the walls. So this is a big problem. Looks very small, but can lead to a lot of bad construction. What needs to be done? I'll come back to you in a little while, but some more pictures. And out here, I would try to acknowledge that these pictures have been taken from another presentation made by friends from the industry who I do not know honestly, but I wish to acknowledge their contribution. So what has happened is that, again, there is the soil below is not compacted properly, filled with garbage, and eventually this is what happens. And the only way to rectify is that you need to reconstruct it. Another picture here. The contractor wished to start the block wall construction here. It rained a day before, and you can see what kind of situation it has gotten into. Mind you, if we had gone ahead and constructed the wall, this entire thing would have to be dismantled and redone. And this is only because that in this portion, which was excavated primarily to make the open foundation, was not filled back properly. One more such picture. So what needs to be done? That needs to be done is that a careful construction has to be done in this area so that this excavated portion is filled back properly in layers and is well compacted. Mind you, this is the portion where the maximum height of wall will come and the maximum loads will be imposed on the foundation here. So it is very, very important that we do this annular filling properly. I hope I'm able to convey my point, and let's proceed further. We go to conformance of design. I think not much emphasis has to be laid on this because every design has certain parameters which have to be met in the field. The angle of internal friction and the density are the 2 important parameters which we all know about. But I think the point I'm trying to make here is the gradation of the backfill, based on which certain design parameters are assumed and not put on the drawings, are generally ignored. For example, here we are using geogrids as the reinforcing element and using a lot of fill which has got a lot of angular material with it. And mind you, once this kind of angular material is placed on geogrids, the damage of the geogrid which will be much more higher than what has been assumed in the design. So it's very, very important conformance to design, not only in terms of phi value and the density, in terms of what other properties of fill material which have been considered in design is important to be adhered to. So much about conformance to design. Internal settlement. When I was discussing with you regarding the connection testing, I told you that this is a major factor which results in connection failures. So how it happens, we'll try to have a look at that. Internal settlement. I think we all understand a typical design section. This is the design section of almost 12-meter height, where we are saying that all my reinforcing elements are put at certain level. My panel is from here to here, which is about 1600 millimeter high, and I put reinforcing elements at various layers. And I assume that the construction would be done as I show in the drawing. Yes, the construction is done precisely as I show in the drawing, but what happens with time is that my strap, my reinforcing element, which was supposed to be at this level, the dotted line level, has actually become in this profile. Why this has happened, you can see that my reinforcing element, which was supposed to be here, has settled by a certain amount. And this amount is a variable, is a function of what kind of backfill I do and what kind of quality control I do on the compaction. One thing interesting you note here is that this entire thing has settled, but this point does not settle, because this is the point where my reinforcing element is connected with the fascia panel. And my fascia panel is not a compressible element. It is compressible, but to a very, very limited extent. If you have seen any RE construction, at these joints, we put compressible bearing pads to make my fascia little flexible, so that my fascia can undergo little compression or settlement, so that whatever settlements are happening because of backfill compaction can be accommodated. But that does not happen all the time. Your internal settlements can be much higher than your fascia flexibility. Proceeding further, this is a recent failure which has happened, and it has happened primarily only and only because of the internal settlements being very, very excessive. This has got the steel hooks as part of the connection system, and even these hooks gave way because the internal settlements have imposed very, very high stresses on these walls. Looking into details, let's go inside the wall. This wall which has happened, which has fallen down, we sent our cameraman inside from there and try to see what is there inside. And this is what he came up with, that my geogrid, which was connected with the hooks, is intact, but has sagged like anything. And how much it has sagged, I will give you the data after a little while. I'll show you the postmortem of the problem. This is the video of the, one second, if I can run the video. Yes. This is inside view of the reinforced soil wall, and you can see that the geogrids have sagged a lot. There is a whole cavity inside the wall. But the point I'm trying to make, I'll try to show you here. See this? This geogrid, which is connected to the fascia panel, is going down like this. And from this point to this point, believe me, is more than 300 millimeters. There are codes available which tells you how much internal settlement can be allowed. BS 8006, clause 643, it very clearly says that it should be understood that the amount of settlement compression within the reinforced volume and to be accommodated by a reinforcing system depend upon the properties of the fill, its compaction, and the vertical pressure within the fill. These pressures are largely a function of structure height and surcharge loading. For walls and abutments, the specified fills, when properly compacted, produce relatively small internal settlements. So it does talk about the type of backfill, the type of height of the structure, and the quality control. And based on this, they have come up with the table 16 in the code, which says that in case I'm using discrete panels, which is the case in the present failure I talked to you about, it says the joint closure of 1 in 150 relative to the panel height. What I understand is that in case I have a 12-meter high wall, 12 meter divided by 150 is the flexibility which I need to provide in my fascia panels, or which the system can tolerate. But in case the internal settlement is more than that value, the problems are bound to arise. And I'll show you this picture. Don't worry about the mathematics and the jugglery here. What I'm trying to show here is that in the current scenario, my differential settlement was to the tune of 420 millimeter here, 430 millimeter, 400 millimeter, 350 millimeter, 300, 250. And this was the portion which failed. So the internal settlements varied from 250 millimeter to 430 millimeters. That means a geogrid which was supposed to be here came somewhere here. So these are manifestation of what kind of quality control you do while doing compaction of the fill. So the compaction of the fill can not only result in settlements, which may affect your riding quality, but it can eventually lead to failures. So that's the point I was trying to make here. Coming to point number 6, preparing for the rainy days. I'll show you many slides and try to tell you that when it rains on an under construction reinforced soil walls, that's the most dangerous thing, that's the most dangerous situation one need to take care of. I'll start with the video. This is the wall already constructed to the height of about 7-8 meters, and then one fine day, a lot of rain happened, and there was no way the water could be discharged, and finally the water found its own way. So all this water, which is coming from above, got in here, it eroded the soil, and all the water drained out from the wall. Okay, and let me show you what happened afterwards. This is where from the wall, all the water got into the wall, and it went out from the fascia panels on this side. So all this backfill was eroded, and all these geogrids, how they look like, finally you can see that. And after that, the only way to rectify was to reconstruct it. Let me show you some more pictures. Another location. It's a corner of reinforced soil wall. The water could not be drained. Water will find its way. And this element here, what you see, is a geocomposite, which has become very, very popular in India. This is a geonet combined with geotextile on both the ends. And this has been allowed in RE wall construction as a replacement of filter media. Now, this is the biggest disaster, I would say, which has happened to the reinforced soil wall construction in this country. This is a economically cheaper version as compared to the filter media, and all the contractors only wish to use it. But anyway, I was coming back to the rainy days. Some more pictures as to what can happen if the rainwater is not discharged properly. A lot of gully formation happened. All this backfill get eroded. The geogrades is exposed. At times, even the fascia panels fall out. And this is all because of rains. Some more pictures. I mean, can someone imagine that if you do not discharge your rainwater properly, what can happen? Out here, the wall was fully constructed. You can see this PCC, which was done for crash barrier. I mean, a few days later, we would have come and placed the crash barrier on top of it. But somehow, the water got into the embankment and found its way out through the fascia panels. You see, such large gully formations have happened. All the geogrids in there is all destroyed. So it's very, very important that we channelize our water properly. And this sketch will try to give you an idea. If I'm building an RE wall here, this is my cross wall, and this is my another long wall. I need to discharge my water through the median. All the water should go slope. All the filling has to be sloping inwards so that all the water is collected in the median and drained out. If you can do this, your problem is solved. But if you allow the water to come out through the fascia panels anyhow, you are in for trouble. So it's very, very important for everyone, and we keep writing in our drawings in very, very bold terms that proper discharge of rainy water has to be taken care of. But in spite of all this, problems do happen, and we face it. And mind you, for all these construction which I shown you, the only repair is reconstruction. I mean, there is no way that you can put these panels back and fill back your backfill. So that was about preparing for the rainy days. Coming to the leveling pad amendment, I think we all understand and we all know that reinforced soil walls, our MORTA specification calls for that the leveling pad has to be at about 1 meter below the outside finish level. Now that's one criteria which should be followed. Otherwise, what can happen is, I'll try to show here. The idea is that it says it has to be minimum 1 meter. And if you do not follow this, this is what can happen. That the outside fill is eroded and your leveling pad is exposed. I'll show you many, many more pictures to highlight my point. Well, already finished highway, crash barrier is done, traffic is flying, and suddenly one day we find that some soil is eroded from the side, and the leveling pad comes tumbling down along with the fascia panel, and all the backfill is flowing out. And this has happened only and only because we did not embed, we did not have our fill at least 1 meter above the leveling pad level. Now, can anyone imagine how this has to be repaired? So it's very, very important that our leveling pad has to be embedded at least 1 meter below the outside finish level. Some more pictures to prove my point. This RE wall was done on a man-made embankment. So what the contractor did, he made the embankment up to the founding level, made the wall, did not come back and refill the 1 meter additional height of embankment which was required on the outside. Rain cuts happened and finally it got exposed. Now, there is no simple repair for all these failures. So it's very, very important that I do my leveling pad embedment at least 1 meter below the outside finish level. Next point, next series of issues we have faced is with running water lines below. What happens, I'd like to show here. This is a flyover in Ajmer. Finished, crash barrier done, only this needs to be done and the traffic would start flying. But what happened is that this is where a water line was running below. You can see this stone here. This is where the water line was running below. And in due course of time, what we noticed is that these gaps started opening. See this? These gaps started opening and we started wondering as to why it is happening. On top, a lot of cracks happened. And on the wall, you can see these joints started opening. And as any normal person, the contractor said, okay, let's fill this up with concrete and the problem would be over. But the problem was not with the joints, the problem was down below because we had buried a water line here, which was running, which is going through the wall. And finally, the remedy was that this entire wall was opened up, this water line was redirected below the flyover, and that's when the problem finished. This was all excavated, this entire wall was redone, this pipeline was diverted below the flyover, and that was the only remedy left. I wish this was diverted before the wall construction. So from that day onwards, we have made it a point that we will not allow any running water pipeline below the walls. But exceptions do arise, and this is one such exception recently in Delhi. But we made sure that this water line was encased with sufficient reinforcement and concrete, so that even if it leaks, it will leak outside my wall, but not below the wall. But I can assure you that there are many situations where the contractor would try to take a shortcut, and as long as they keep taking shortcuts, the problems will keep arising. So far I have covered 8 points. Coming to the next points, which are unused pipes, the structure below. Nothing much to say. Only thing I want to say is that in case you find any unused structures or pipe below where you want to build your RE walls, kindly have them excavated, removed, filled back with good compaction, and then build your walls. Crash barrier and friction slab on RE walls. Another very interesting topic. This is how we do precast crash barrier. This part of the system from here to here is precast, and we are left with some dowels here. And this part of the friction slab is done in situ. Very important, because this in situ connection is what is holding all these individual pieces together. Try and imagine a situation where you will have a vehicle hitting this crash barrier. It has to have certain amount of resistance to to that force, and that the resistance will not come if this piece is sitting there individually. This piece which is taking the hit has to get support from all these adjacent units, and which will happen only in case you do a in-situ stitch. At many situations, the entire piece from here to here is precast without any connection with the adjacent unit. That is a blunder. Please do not allow that. We must have an in-situ stitch, which will be stitching all these individual pieces together, so that once you have a vehicle hitting, all the units would be acting in unison. See that? Again, this is an in-situ stitch we are doing. And this is the problem solution. The solution to the problem I was telling you about, that we are putting these turnbuckles here so that this precast piece is not transferring any load to the panel below. If I don't use these turnbuckles, this piece is not stable by itself, and it would go and rest on the panel below. So as long as I'm using these turnbuckles, I am not allowing it to rest on the panel below. I did tell you that in case you are doing a full precast unit, it is still possible to do in case you are able to manage connections with the adjacent units. So this is one such construction where you have the shear keys designed to engage the adjacent units when one unit is taking the vehicular impact. So you have male shear keys, two kind of shear keys on one side, and you have the female shear keys on the other side. If you do that, it is equally good to an in-situ connection. In spite of doing these in-situ connections, at times we have seen in recent past that once you have a vehicle hitting a crash barrier, you can still face problems. This is a photograph of the same location, but from 3 different angles, from a wider angle, from a closer view, and you see this pipe here. This is the view from the side of the road of the same thing. When this happened, mind you, there was no distress on the road surface. Only this crash barrier has failed. Why it has failed, I'd like to get into it in a little while. This is how a typical crash barrier with friction slab looks like. And my road surface is somewhere here. This is a structural crash barrier which is connected to the friction slab down below. Once you have a vehicle hitting here, it will try to overturn, and this friction slab here along with the dead weight will try to resist. In the present case, what I feel is that this crash barrier has failed from here. It has failed from here because at times the design is done in such a way that there is a necking happening here. And in case there is a necking happening here, this part of the crash barrier will rotate. It will fail from here, and it will fail to mobilize the resistance which is provided by the friction slab and the overburden here. And I think this is what has happened here, because in these cases, once you inspected the road surface, there was no sign of any distress. That means this system of resistance was not mobilized, and this crash barrier broke from here, and it overturned. So two things very, very important here. One is that not only this part has to be strong enough to carry all these loads, there should not be any knacking happening here. If there is a knacking happening here, then the crash barrier will not be able to mobilize the support. Moving further, I think this slide I've already shown you that since this piece is not stable by itself, you are deriving the support from the fascia panel, which is absolutely incorrect. If they had used turnbuckles here, then this piece was stable without deriving the support from the panel here. So this is what should have been done, but did not happen. Okay, I think I've already said about this. Resting on the fascia panel, this corbel, which we discussed some time back, that should be incorporated. This is my request to all my structural engineering friends. Coming to the use of geocomposite, and as already said, this is a big no. The economy is deriving use of this product, but I don't think this is a very, very good product for at least the reinforced soil walls. If you want to put it behind the RCC walls, no problem, but not good for RE walls. We would like to go back to the filter media concept, which is much better to what I said here, which was much better to the geocomposite. And why it is so, I would like to highlight using another slide. This slide basically shows you again the phenomena of internal settlement. In case you don't have a filter media here, this is how your geogrid profile would, or a reinforcing element profile would look like, as compared to in case you have a filter media in place, because filter media is a self-compacting material. And what we have been seeing that even with this, without the filter media, whatever best you do, there is still some portions which are left uncompacted because you have some hooks, etc., coming out from here. There is no way that this roller can go very, very close to the panel. So at least 6 to 8 inches of soil of the backfill is left absolutely uncompacted if you're using geocomposite. And this is what is leading to problems of this kind, where this internal settlement, which should have happened like this, is happening like this. So I am personally against use of geocomposites, and given a chance, if somebody wants to consult me and you guys, kindly try to avoid it. Ground SBC availability. I need not emphasize more on this issue. I have already shown you some slides, but the only point I am trying to want to make here is that generally as RE wall vendors, we are given this backfill information only for the abutments, and then we try to extrapolate the report for the abutments for the entire length of the wall, which is not a good practice. I think we need to have not only trial pits, but also bore logs for the approaches, which contractors do, but they do only once they are asked for. Otherwise, they'll give you the abutment soil restriction report, and you will need to make the best use of it. This slide I've already shown you. I need not emphasize it more on this. The next point is the use of steel strips versus geosynthetics. Why I have taken this point up is, according to me, whether you use steel strips or geosynthetics, I don't see any change in the performance of the walls. So this is my personal opinion that there are many contracts in certain state PWDs where they say, no, steel strips only have to be used, and no geosynthetics. Probably they are of the opinion that if you make something with steel, it's going to be more durable and more long lasting. But I think my opinion is that in the final performance of any normal construction, there is no difference between steel strips and geosynthetics. Coming to the next, we're coming to the end of the presentation, gentlemen, but a couple of points left. Heavy equipment usage. Well, it should be avoided very close to the walls. I'll show you a couple of pictures. This is a picture from a recent project of ours where we finished the walls and the contractor has to launch the girders, the precast girders onto the spans, for which he installed a crane on top of RE wall with no safety margin from the cross wall. And you can see this is what happened. See this? You see this point here? When the crane was lifting the girders, the support gave way because this high load was very, very close to the panel. So this is something which we learned the hard way, and later on we had to open it and redo the construction. Vendor pre-qualification, I think this is not a technical point, but more of a commercial point, but I strongly feel that if the departments are going in for vendor pre-qualification, this will avoid a lot of issues. This would avoid the divided responsibility. And if the contractor or the departments are able to get one-stop solution, probably that would be the ideal thing to happen. Pareto principle, I'll try to run through it quickly. Pareto principle is actually, it says that is known as the 80-20 principle, which states that for many events, roughly 80% of the effects come from 20% of the causes. And I'd like to give you some examples that 80% of the sales come from 20% of the clients. 80% output is from 20% of the staff. 80% of the wealth is with 20% of the population. 80% errors are eliminated by removing 20% of the bugs. And this is what I thought I'll pick up on, that 80% errors are eliminated by removing 20% of the bugs. And what I intend to do here is that I have given you 15 areas where we need to review, where we are facing problems. And I only need to remove 20% of these. I need to review only 20% of the areas. And I feel that out of 15, if I really review the 3 areas, my many problems would be over. And these 3 areas are actually conformance to design, preparing for the rainy days, and vendor pre-qualification. I thought that these are the 3 key areas where if we take care of these 3 key areas, many problems would be taken care of. So gentlemen, with that, I'm coming to an end of the problem. I mean, not the problem, sorry, coming to the end of the presentation. And again, those who wish to connect, these are my contact details here. And I hope I wish to hear from you. In case you have any questions, you can WhatsApp to me, or you can write to me, or you can connect with me on the LinkedIn. So gentlemen, during these lockdowns, please stay home and save lives. Thank you so much. Thank you.
Thank you so much, sir. It was excellent presentation. Very interesting and very well put.
Thank you, sir.
What I think is, if anybody already, because of some technical thing and others, we have tried to record the presentation and we'll be sharing. However, if anybody has a query, then you can please type in the message box, and we can take 1 or 2 queries maybe. Rest can be emailed and they will be responded.
No, I have not seen anything. Well, there is nothing on the WhatsApp with me. If you have anything, probably we can take up those.
Is there any query? You may please type in the chat box on the side.
Vikas Patil says,
I
what is
think
the future of RE walls in India? I think the future is bright. Nothing to worry. Every industry should learn from what the experiences have taught them. Bhumi Kamdar says, does backfill soil undergoes any deformation due to temperature changes? I have my doubts. Please put the mobile number again. I'll speak now. This is 9899222244. 9899 4 times 2, 2 times 4. Mr. Chandra says, any precautions from flood water? Generally, the walls are designed and constructed for dry conditions. That means that we do not generally expect them that they would get flooded or they would be submerged. In case you have any situation like that, then a separate design has to be carried out for them, and a very good granular backfill has to be used for such walls which are likely to be flooded. Mr. Subramaniam says, what would be the ideal height of RE walls, as walls greater than height in the order of 9 to 12 meters have failed? No, I don't agree with that, sir. We have constructed walls ourselves up to 17 meters without any problem. But we have seen failures happening in 4-meter height wall also. So let's not blame the technology for the failures. Mr. Nirav says we need to relook the design and redesign in walls as per Indian environmental conditions. I don't know what to say on that. What is the maximum height of retention of RE solution you provided till date? I think we've done up to 17 meters. It is
any
required
experience?
to calculate immediate settlement in RE well. It is not immediate, this is internal settlement, and we don't need to calculate that. Dr. Shade, you can tell me when to stop, please.
Yeah, sir. I think at this point we should stop, and I'm noting down all the other questions, and will be emailing you. The respondents will be the responses to the questions will be emailed to the questioning person.
Okay, ji.
So
Thank you.
thank you very much, sir. Really a very interesting and very knowledgeable presentation. I apologize to all participants for whatever little technical glitch. We'll see how we can make up in the video. Thank you. I'm
Thank
leaving
you,
now.
ji. Thank you. Thank you.
Thank you, everyone. I am leaving now. Thank you very much for your patience and good company. I will try to send the video over to you, and in case you don't get it or some glitch, because sometimes the email bounce back, then you can feel free to email in person to the anal.iastructe@gmail.com. Thank you so much.